Hello everybody, I am Zach Peterson. Welcome back to my channel. Today I'm going to run over every single PCB design calculator I have ever created. Now if you've watched me on the Altium Academy channel, you know that I've produced a ton of calculators over the years. Some of them are embedded into the Altium website, some of them just exist as Excel sheets. And I've never actually taken all of this stuff, compiled it into one location, and put it out there for the public. So that's what we're gonna do today in this video. If you check out the link in the description, you'll find a link where you can download all of the Excel sheets that I show in this video. It also includes links to the calculators that I've embedded on the Altium website. And with that in mind, let's go ahead and jump in and see all of the design calculators that I've created over the years. Let's get started. So let's go ahead and just jump right in. The first calculator that I want to show you is the transmission line calculator. And the transmission line calculator is intended to calculate transmission line impedance and propagation constant with losses. So here you can see on screen we have some of the equations that we're going to use to calculate the impedance. And of course the basic equation for characteristic impedance of a transmission line is given right here. It is Z0 and it includes all of these loss terms. We have a resistance, we have an inductance, we have a capacitance, and then we have a conductance term that includes the loss tangent of the dielectric material. Now here, this inductance term also includes the copper roughness constant and it includes the skin resistance. We have the same thing here for the transmission line resistance. You can see here that we have a DC resistance and then we have a frequency dependent skin effect resistance. Now I've done some math in some articles and in numerous presentations overseas in Europe and at PCB West where I show how to derive a lossy transmission line impedance equation and propagation constant, which I've shown here on these slides. So if you want to get access to that material, make sure to get a hold of me on LinkedIn and I'll point you to where some of those resources are located. So I'm not going to run through the whole derivation in this video, but you can see that these are the equations that define the transmission line impedance with loss and the propagation constant with loss in terms of a lossless impedance function. Now this is really important because that lossless function could be, for example, Waddell's equations, or it could be the IPC 2141 equations, or it could just be an empirical model that you have available from measurements, or it could be the value that you pull out of a calculator, for example, in the Layer Stack Manager in Altium Designer. Regardless, you have a lossless value and you can plug that into this equation along with all of these other material parameters, and that's going to give you the lossy impedance and the lossy propagation constant. Now the calculator that I've built for these equations is shown right here inside of Microsoft Excel. And here I've built the model for strip lines using Waddell's strip line impedance equations. But of course, you could also do this for the microstrip equations using the equations in Waddell's textbook. So you can see here what's going on in this calculator, and it is pretty extensive, but I'll do my best to walk through this. So here you can see that we have our frequency range that we're considering. You can see here that we have a real and an imaginary dielectric constant. You can figure those out just by looking in data sheets. You can do interpolation. You can use, for example, a wideband Debye model, or you can just use a constant value across your entire frequency range. And then you can see here we have our geometric parameters, which ultimately give us our lossless impedance. Then, once we add in all of the other terms, we then get to our lossy impedance, as you can see right here. We then add in the skin effect resistance and the roughness, and then that gives us our total impedance. Now the reason I originally built this was so that we can do an optimization procedure where we basically converge to just the right amount of width in order to balance the real part and the imaginary part of the lossy transmission line impedance against some target impedance, which is typically taken as 50 ohms. And the result can be seen right here in this graph. So this graph shows you generally what the transmission line impedance tends to look like over a broad frequency range when you consider all of these factors from skin resistance and the dispersion in the dielectric constant. So take a look at this graph. You can see that the real part of the impedance tends to increase in this upward curve fashion, and this is exactly what I've shown in some other videos on the Altium Academy channel and on my channel when you look at the impedance once you start to include these other loss factors. You can then see here on the right hand side what is the scale for the imaginary part, and then the dashed line here shows the imaginary part of this impedance. Now I've built multiple versions of this calculator, and you can see I have an old version here in this tab, and then you can see here there's an inverse Fourier transform version in this tab. But here, the one that gives you the best resolution is here on the Stripline Fine tab. So this Stripline Fine tab includes much higher resolution on the frequency range that we're considering in this transmission line design. And if you scroll over here to the right, you can get a little bit of a better idea of what happens with the impedance over various frequency ranges. And you can see here, it looks like it has very high impedance starting out at low frequencies, which is exactly what you would expect from the model that we showed earlier. And then you can see here that it reaches some minimum and then eventually starts to slope upward again due to the skin effect resistance. You can also see here that it calculates a return loss and an insertion loss. So that's what's shown here in this view. So go ahead and take a look at this calculator, play with some of the geometric parameters, and you can see if you can use the solver tool inside of Microsoft Excel in order to converge to an optimal transmission line design. Next calculator I want to look at is the copper versus dielectric losses. Now this slide that I have here on screen is also something I've shown on the Altium Academy channel, and I've shown it in some of my presentations in the past. And this slide is basically showing you a comparison of the dielectric loss versus the conductor loss for smooth conductors and rough conductors. Now the purpose of this copper versus dielectric losses calculator is to be able to compare when is the dominant loss mechanism due to the dielectric material, or when is the dominant loss mechanism due to the skin effect in copper as well as the roughness in copper. Now you can see some example results here on screen, but the important part here on screen is this little formula right here at the top. So this little formula tells you that the total loss is just the sum of the conductor loss and the dielectric loss. So if you have a calculator like this and you know that the conductor loss or the dielectric loss is the dominant loss mechanism, you can then take a PCB that has too much insertion loss on certain transmission lines and then determine whether you need to change out the material for the dielectric or do something different with the copper, such as use smoother copper or increase the width of the traces. So here you can see what this calculator looks like. Here I have a version for stripline loss, and then I have another version for microstrip loss, and I have the microstrip loss up here on screen. And this loss calculator uses the Hooray model for the copper roughness. So this lets you do two things. First thing it lets you do is compare the copper and the dielectric losses together on the same graph, and you can see that right here in this left graph. The other thing it lets you do is experiment with different values of roughness, and then you can really see how roughness affects the total loss over this frequency range from 0 to 20 gigahertz. You can also very easily extend this beyond 20 gigahertz just by changing the frequency range here in column A. Finally, we also have a graph here for the total loss, which is again just the sum of these two losses, and this lets you see just as an estimate what the total loss will be over this frequency range on a transmission line that's designed with this calculator. Now you'll notice here in the upper left corner we have two cells for the inductance and the capacitance per unit length of this transmission line, and that's what's used to calculate impedance. So where can you get those two values? Well, you can actually find those two values inside of Altium Designer in the Layer Stack Manager over in the Properties panel. The calculator inside the Layer Stack Manager uses Symbian in the back end, which is one of the best PCB calculators you'll find on the market. That calculator will give you these numbers for the inductance per unit length and the capacitance per unit length. All you got to do is copy those numbers here into this calculator, and then it will generate all this stuff in these graphs. Next calculator that I have is a critical length calculator, and one of the reasons I developed this calculator is basically to show that the critical length rule that's often cited by AI in PCB design content is frankly, total bullshit. It's not that the critical length is bullshit as a concept. It is actually valid as a concept and as an analysis tool. It's really just that the selection of various critical length values is kind of arbitrary. So the typical description of the critical length rule states that if the length of a trace is less than 25% of the length traveled by a digital signal during its rise time, then the trace impedance does not matter. So then it follows that if the trace impedance doesn't matter, you don't have to worry about reflections when the trace is short enough. Now that 25% length factor is just one of 9 different values that you will see cited out there in various PCB design guidelines and application notes. So some of the other critical length factors include 1/2, 1/3, 1/5, 1/6, 1/8, 1/10, 1/12, and 1/20. So let me ask all of you this. If there's a design rule that has 9 different values that you should follow, do you think it's a very good design rule? I'm going to guess that you're going to say 9, 9, 9, 9, 9. Now the reality is that the actual value for a critical length depends on the impedance deviation that you can accept between an input impedance and a source impedance or a target impedance. Now the result of this calculation is that any apparent correspondence to the rise time or dependence on the rise time is actually totally arbitrary. All that really matters is the length. Now you can convert the length to a rise time using the speed of the signal or using the speed of light along that interconnect, and that will give you a rise time. But what really matters is the length that the signal travels during the point where it's switching. So a typical critical length calculation result looks something like this. Essentially what we're calculating is what is the ratio between the target impedance and the input impedance of an interconnect as a function of the length or the rise time length. And what you see here is that when we can accept a 20% impedance deviation, we can identify multiple possible critical lengths. You can see here that we picked out a 25% critical length and a 28% critical length and then a 40% critical length. And you can see here that these different values correspond to different trace impedances. So the critical length actually depends on the actual trace impedance that you've put into your PCB. So it's a bit ironic that somebody would say, well, we don't have to worry about the trace impedance, but in order to figure out whether or not you need to worry about trace impedance, you have to actually calculate it. It's a bit backwards and convoluted, I know. Similarly, if you can only accept a 10% maximum deviation in your input impedance, you'll see that the critical lengths for these signals tends to be shorter. So at a 10% impedance deviation, you'll see here that we can only accept a 10% critical length for an 80 ohm line, whereas we can accept almost a 20% critical length on a 60 ohm line. So here's the calculator that actually gives you this result. You can see here that I have both of these examples programmed into this calculator. Here we have the 1 gigahertz example and then our second 1 gigahertz example shown down here. And what you can do is put in different values for transmission lines and a target impedance, and it will calculate the input impedance, and it will give you a percentage deviation from your target impedance for that input impedance. So this 20% tick on this graph says that the input impedance of this line is 60 ohms, even though we're targeting a 50 ohm impedance. So in order to use this calculator, you need to have an actual line impedance that you're going to use in your board. Here in this example, it's 80 ohms. And then you would need to have a target impedance for your load. In this example, it would be 50 ohms. So in order to use this calculator, you need to input 2 parameters. The first parameter that you need to put in is the line impedance. The second parameter that you need to put in is the target impedance or the terminated load impedance. So here the line impedance that we're using is 80 ohms, and then the load impedance or the target impedance is 50 ohms. The calculator then calculates the input impedance, it then calculates the deviation from that, and then it displays the results on this graph as a function of length. So from this graph, if you can accept a 20% input impedance deviation, that allows you to pick off the critical length value for this 80 ohm line. And what it tells you is that your critical length value for this 80 ohm line is basically 24%. So pretty close to that 25% value that's stated as a rule of thumb. Now the next calculator I want to talk about is tapers. And of course, you might be wondering, what is a taper? Well, a taper is a printed feature that essentially creates a minimally reflective transition between 2 different impedances. So here on the left, you can see we have a narrow transmission line with a high impedance, and then on the right we have a wider transmission line with a lower impedance, and then the taper design problem is essentially what is the shape that this taper needs to have in order to be below some reflection limit. So this is solved by essentially plugging an impedance profile into this integral equation and then solving the integral. Now this problem is a little difficult because there aren't always analytical solutions to this integral problem. Normally, when you have an integral that doesn't have an analytical solution, you would take this problem, put it into MATLAB, and then have MATLAB solve the problem numerically. Or you can do what I did, which is build a spreadsheet which implements a numerical procedure to solve this integral. Now there are some common impedance profiles that you can use. Here, for example, you have the linear profile, you have an exponential profile, you have a polynomial profile, or you have another profile called the Klopfenstein taper, which we're going to look at here in just a moment, which is based on modified Bessel functions. Now here you can see what an impedance profile and a width profile looks like. And so when you have a linear impedance profile, that doesn't mean that you have a linear width profile, but you can usually approximate the width profile as a straight line, as you can see here in this graph. So there is a little bit of curvature in this line in the blue dots, but you can see here that it would be appropriate to more or less approximate this as a straight line. And then there is one impedance profile that does admit an analytical solution, and that is an exponential taper. So an exponential impedance profile will give analytical solutions that essentially look like a sinc function. So let's take a look at the calculator. Here you can see I brought up the taper profile calculator for a microstrip taper, and tapers are generally used on the surface layer to connect microstrips to a load or to connect two different microstrips to each other. Here on the right hand side you can see here that we have that graph which I showed in the presentation, and then you can see here we have all of the data that we would use to then calculate everything that we need for our taper. So the inputs into this taper calculator are the trace thickness, or the copper weight. Here all of the units are in meters, so we have a trace thickness, and then here we have a substrate thickness. Here it's, for example, 0.1 millimeters. We have a dielectric constant for our substrate, and then we have a target length for our taper. Here we also have an operating frequency, and then here we have this interval term. And this interval term tells us basically how does the width change in each of these 30 steps that we have defined here in column A. So by setting an interval value of 0.15, that allows us to vary the width from 4.6 mil all the way up to 9.13 mil. Now if I change this interval value to 0.2, you can see here it changes our width from 3.88 to about 9.88, and you can see here that it calculates the reflection coefficient for this taper. So we would expect a reflection coefficient coming into this taper of only 20%. Now the next thing I want to look at is the Klopfenstein taper, and this Klopfenstein taper calculator, I actually did not create this. This calculator is available on everythingrf.com, and I will include a link to this calculator in the video description. Now the Klopfenstein taper is important because it has the theoretical minimal reflection coefficient that you can have for any taper that you might use in a planar system, such as in a PCB. So go ahead and check out this calculator because it is very easy to use. Essentially what you do is you put in your two impedance values and you put in your maximum reflection coefficient that you can accept, and it will calculate a taper profile for you. Now practically in PCB design software, the easiest taper to implement is a linear taper, but you can use a drawing application like AutoCAD to implement a curved taper such as the Klopfenstein taper or an exponential taper. Now the next calculator I want to look at is the Substrate Integrated Waveguide calculator. And what is a Substrate Integrated Waveguide? Well, a Substrate Integrated Waveguide is essentially a structure that allows propagation with specific electromagnetic modes. And if you're not familiar with what an electromagnetic mode is, go Google it and learn about transverse electromagnetic modes, transverse electric modes, and transverse magnetic modes. So you'll need to understand those concepts before getting into substrate integrated waveguides. But essentially what this does is it allows you to calculate all of those electromagnetic modes using a very simple set of formulas. Now here's what a substrate integrated waveguide looks like on a test board, and this is something I've shown in various presentations over the years. And you can see here what this test board looks like. We have an SMA connector on the edge. The pin then touches a microstrip. The microstrip goes into a transition using a taper, and then that feeds the signal into this substrate integrated waveguide. Here on the right-hand side, you would have emission at a very specific electromagnetic mode, which could then couple into, for example, a metallic waveguide. And that's actually the most common example, or the most common application where I have used this type of interconnect design. So here's the basic geometric model for a substrate integrated waveguide that you can then use to calculate all of the geometric parameters that give you optimal signal transmission into this waveguide. So here you can see the calculation process here on the right. I'm not going to go through each step. Instead, what I'll do is just jump into the calculator and then show you how you can use that to calculate all of the different cutoff frequencies for the various electromagnetic modes. Now, before we jump into the calculator, I have here a process for a 5.8 gigahertz Wi-Fi signal that is being transmitted into a substrate integrated waveguide. So here you can see all of the calculation results for a 5.8 gigahertz signal. Here we get the equivalent width of this waveguide. Here we have some data for the dielectric constant. Here you can see we have some via data that we use in this model, and then using the via diameter and pitch, we can then get the actual value for the spacing between the vias that defines our substrate integrated waveguide, and then we get our allowed frequencies using this wave number value. And essentially what you get at the end of this is a table with a bunch of modes. And so what this tells you is which of the allowed modes are allowed to propagate through the substrate integrated waveguide. And once you know the allowed modes, you know exactly what the spatial distribution is of the electric and magnetic field inside that substrate integrated waveguide. Here in green, we have all of the geometric parameters that we are plugging into these equations that define this geometric model. And then here above this, we have some of the data that we're using to calculate the impedance of the microstrip that connects to this taper and then connects into the substrate integrated waveguide. Now the table that gives us our cutoff frequencies is right here, and I'm going to go ahead and put a little box around this. Now this table tells you what are the various cutoff frequencies for all of the different modes in this substrate integrated waveguide. And you can see here we have a 4.5 gigahertz cutoff frequency for the 1-0 mode in this waveguide. You can see here that as we iterate through these different cells in this table, eventually we can get up to very high frequency mode propagation in this waveguide. So this is basically the same type of calculation that you might do with like an optical fiber or even with a coaxial cable that's operating above the TEM mode. Now the rest of the calculators that I want to talk about in this video are actually not done in Excel spreadsheets. They are embedded in the Altium website. So here I have a list of calculators that you can see on screen. We have an IPC 2152 calculator. We have two IPC 2221 calculators. And then I have a set of impedance calculators for strip lines and microstrips, both single-ended and differential. And then we also have a patch antenna calculator. So I'll go ahead and jump in and briefly give you the overview for all of these different calculators. So first, let's take a look at the IPC 2152 calculator. Essentially what this calculator does is it tells you how much copper you need to have in order to limit the temperature rise of a current carrying piece of copper below some maximum value. So if you scroll down here, you'll see that there are several parameters you can input. Here we have a current we can input. We want to limit our temperature rise to 25 degrees C. We can select the copper weight. We can select our total PCB thickness. We can specify whether there's a plane nearby this rail, and we can specify our plane area and our distance to the plane. And you can see here that it returns a rail width and the total copper area that we need in order to ensure that our temperature rise is limited to 25 degrees C. Now there is a similar calculation procedure or formula specified in the IPC 2221 standards. However, as I have discussed with other experts in the field, and in particular with Mike Jopi, who helped develop the IPC 2152 standard, the 2221 standard is way overly conservative. Now, if you plug in similar numbers into this calculator, you will find that the copper area that you need to have for the same temperature rise limit with the same amount of current is actually much larger. So here we can just do a quick experiment. we can go ahead and put in our same 25-degree temperature rise at 20 amps, and you can see here that the copper area and the rail width is much larger. Now, limitations on trace heating as a function of trace current are also defined in the IPC 2221 standard, but as I've discussed with Mike Jope, who actually helped to develop the IPC 2152 standard, the 2221 standard produces some, I guess you could say, not necessarily non-physical results, but overly conservative results. Now, if we scroll down on this page, you can see here where we have our fields where we can input our data for this calculator, and you see that we need some of the same information. Here we need to have a current that's specified and a temperature rise that we would like to stay limited at in this interconnect. So we're actually inputting less information into this calculator, so we're actually a bit less granular compared to the case of the IPC 2152 calculator. Now, based on real measurements, the IPC 2152 results have been found to be more accurate, but I'll let all of the viewers out there who are going to do any sort of thermal design and evaluation to be the judge on which calculators are going to produce more accurate results. The other IPC 2221 calculator that I have here is a clearance calculator for high voltage design. And you can see here that we have a few different tables and calculators that are located on this page. Now, the calculator here is for the IPC 2221B standard and another standard, which is the IPC 9592 standard. And so this calculator is telling you how far apart you need to space pieces of metal in your PCB in order to prevent arcing and prevent other reliability problems. This is defined using an AC or DC peak voltage, and of course that makes it very easy to use. For example, we can just put in a 480 volts, and you can see here it immediately gives you a value for spacing for external traces and for internal traces, as well as coated traces. So this would be like traces that are coated with a solder mask. Now, recently there was a new revision of the IPC 2221 standard that was released, and that is revision C. And in revision C, there are some additional definitions for conductors that are used to then determine the required clearances between conductors at different voltages. And that data has been compiled into this table, and this was done by Caleb Buck, who was one of our Altium On Track podcast guests. Here, again, you just do the same thing as in the previous calculator, put in a peak AC voltage or DC voltage, hit the calculate button, and you can see here it gives you all of those different clearance values for each of these different categories that are defined in this table. Now, the next four calculators are all impedance calculators. Here we have single-ended impedance, differential impedance for microstrips, and then single-ended impedance and differential impedance for strip lines. So these should be pretty self-explanatory. If we just scroll down here, you can see that you just put in all the geometric parameters for the copper and for the dielectric thickness and for the dielectric constant, and then it will give you impedance values for each of these situations. So I'm not going to belabor this. Go ahead and jump onto these pages and play with them. And if you like, you can compare the outputs that you get here with the outputs that you would get from a tool like the impedance calculator in the layer stack manager inside Altium Designer. And the last of our impedance calculators that I want to go over is the Microstrip patch antenna calculator for RF designs. So this Microstrip patch antenna calculator essentially tells you what is the input impedance looking into your patch antenna, what is the bandwidth of your patch antenna, and what is the required width and length of your patch antenna for a given substrate thickness, substrate dielectric constant, and operating frequency. So for example, if we have a DK 3.5 laminate, it's 5 mil thick, and it's operating at 10 gigahertz. We just click the calculate button. You can see here what is the input impedance. You can see here what is the bandwidth at which that input impedance is valid, and then this is what the width and length of that antenna needs to be. Now, oftentimes, in order to get a feed line into a patch antenna, you will actually inset the feed line just a little bit, as shown in this image. Now, typically your feed line is going to be 50 ohms because the component that is broadcasting that signal is probably also set to match to 50 ohms. So you then need to have a match between the 50 ohm feed line coming into the patch antenna and the patch antenna's input impedance of typically a high impedance value, such as the 275 ohm input impedance that we calculated here for this example. Now, if you just scroll down here, you'll see here some values for the input impedance. In this example, we had an input impedance of 275 ohms, our feed line impedance, which we're going to set to 50 ohms, and then our length of our antenna, which we can then copy from this value here in the previous calculator. So we're just going to copy and paste that in here. And then what it tells us is the depth that this feed line needs to be set into this antenna. Now, the last piece here is this spacing value. What does this spacing value need to be? Well, here I've provided some guidance on what the spacing value typically takes. And typically it's 1 to 2 times whatever the width is of the feed line that's coming into your antenna. So in this example, if we had a 10 mil wide feed line coming into our patch antenna, we would have 10 to 20 mil spacing between the feed line edge and the antenna as shown here in this drawing. Now, if you want to find the links to these calculators, again, check the video description. I've put all of the links to the calculators in the description, as well as a link to download all of the Excel sheets and the slides that I showed earlier in the video. Thanks for watching this video, everybody. Make sure to hit the like button, hit the subscribe button, make sure to check out those download links, and I'll see you all in the next video.